All right, awesome. Thank you so much. So thank you everyone for joining today. Welcome to the hands-on bootcamp in computer vision. I have a very specific agenda in this bootcamp, which I will mention what exactly we will be covering in this bootcamp. Who is this meant for? What can you expect to get out of this, etc. So before that, let's spend a little bit of time. I can introduce myself a little bit. My name is Sridhar Panat. I am one of the co-founders of Visuara AI Labs. So my education was from IIT Madras in 2012 to 2017. And after graduation, I went to MIT for my PhD. So that was from 2017 to 2022 for 5 years. And then after graduation, so my PhD was mostly in interfacial engineering, little bit of electrical engineering, little bit of machine learning, robotics. So it was like an interdisciplinary field of many different things. And I had a lot of fun time during my PhD. But after that, or I would say slightly before that, we ended up working together, Raj, Rajat, and myself. You might be familiar with them through LinkedIn or our YouTube channel. So we decided to start Visuara to basically do many things in the AI domain. If you are interested, you can check out this video. This is a 3-minute video of my PhD thesis work, which was published on
located in desert region.
MIT's YouTube channel. It has almost 300,000 views now. So my basic work was to build a self-cleaning solar panel, which can remove dust and clean itself and recover almost 95 to 98% of lost power output. Because when dust is accumulating on solar panels, which is very likely in desert settings, it can drop the efficiency significantly. So this was like a waterless electrostatic self-cleaning robotic system. So it can clean it can clean solar panels without having the need for a single drop of water. The interesting thing was, while working on this project, inadvertently machine learning entered the picture, because there was something called as dust removal voltage. So dust removal voltage was how much voltage per centimeter do you have to apply to charge and repel a particular particle of, let's say, 30 microns in size or 50 microns. There are particles of different sizes. So this dust removal voltage was completely dependent on the particle size. Now, how do you know the particle size? You don't know, right? You can't take a microscope and check the particle size in every single region of a solar panel. So what is a sensible thing to do? So I purchased a very cheap camera, which could get 50x to 100x magnification. So it was not as good as a proper microscope, but it could magnify a little bit and give me like thousands of dust particles in one single frame. Now, from this single frame, I wanted to get a dust particle size distribution, especially its mean and standard deviation, so that I know that, okay, most particles are in this size bucket, so that the dust removal voltage could be applied, whether it is 10 kilovolt, 12 kilovolt, 15 kilovolt, whatever that is. And how would you do this? Are you going to count? Are you going to fit circles around every single particle and measure the average size distribution? No, you won't be doing that. Here is where machine learning enters the picture, especially computer vision. So I implemented a convolutional neural network, which could real-time process the images coming through camera. And then this can classify the dust particle sizes into different buckets. So 30 micron bucket, 50 micron bucket, etc. And based on that, my autonomous solar panel cleaner could decide what voltage to apply. So this was an interesting use case of computer vision, or specifically deep learning in computer vision, for a complete hands-on physical experimental setup and a product. So I just wanted to share this with you because I'm pretty sure that people in this call will have background not just in computer science. I'm sure you are from different backgrounds like mechanical engineering. Some of you might be from computer science. Some of you might be from totally different, not even engineering background, right? And you might be wondering, why is deep learning, computer vision with deep learning relevant to you? It's relevant because I just wanted to show you this example to show you the relevance, but it's anyway relevant because the field of computer vision has penetrated into various domains in various industries. I will show you in today's lecture some of the example industries. So this was just my introduction. And I'll also mention one more small story of how what was one of my initial research attempts at traditional computer vision. So this was more than 10 years ago when I was an undergraduate student. So we were working on a problem for classifying rice grains. So if you have a bunch of rice grains on a surface, there are many different varieties. There is basmati rice, jasmine rice, ponni, idli rice, and there are many dozens of varieties of rice grains. On an average, these grains have an average size. There is a distribution, but sizes differ based on what rice grain variety it is. And there are many configurations in which rice grains could be on a surface. Sometimes it could be sparse. It could be distributed such that there are only few grains on a surface on any image, right? Or they could be on a heap. So there are many rice grains touching each other. So at that time, although deep learning had slightly entered into the scene, thanks to AlexNet, which we will discuss a little bit, the traditional computer vision approaches, which had nothing to do with deep learning, was still prominent. So what were we trying to do? We were trying to do something like ellipse fitting. So let's say you have a rice grain that looks like this. These are actually in the image when you perform some kind of thresholding. So when you convert an image into pure black or pure white image, you may notice features, shapes like this, which are not representative of an actual rice grain. So what could be happening? What could be happening is two rice grains are touching each other. So you have to first figure out under what conditions, what is an algorithm which can detect when two rice grains are touching, because their outline will be just one single shape, and then split those shapes into two different shapes, find the center of mass or center of geometry of those shapes and fit ellipses, then calculate the length and the breadth of this ellipse, and then plot this size distribution such that this could be the longer axis, let's say B, and this could be the shorter axis, or vice versa. And then what will happen is rice grains of similar varieties, let's say idli rice, may be distributed here, and then maybe another variety of rice may be distributed here. So this was a pure traditional computer vision approach, which had nothing to do with deep learning. Neural networks were not even in the picture. But this could have been done with neural networks also, right? As we famously know now. But the good thing is this paper got us a really good exposure into various techniques that were happening in machine vision and computer vision at that time. This work was accepted into the 9th International Conference on Machine Vision, which happened in Nice in France. And it was very clear to us when we presented our work in that conference that the research community is entirely going to shift in the near future into deep learning based approaches for computer vision. Nobody is going to work on hand engineered features. And this major shift I was so lucky to experience this major shift almost in real time. Of course, there were other shifts that had already happened in more, deep communities in computer vision or in computer science. So AlexNet was the paper which came out in 2012 that showed for the first time that, and this was in 2012, and this paper showed for the first time that you could use deep neural networks for training on large data sets of images. And they even used GPU for training. So it showed for the first time that you can leverage parallel computing to make everything faster. And if you look at the NVIDIA's stock, right, the rise of NVIDIA's stock, everything, it can't be attributed to one single event, but if it can be, then this would be one of those events. The proposition of AlexNet. So Alex was the name of the first author of the paper. Then there was Professor Geoffrey Hinton, who won Nobel Prize in physics for his work in neural networks. This was in 2024. And Ilya Sutskever was also there. He's one of the founders of OpenAI. So this all was happening in 2012. And then people had gradually started to eliminate hand engineered features from their work. So how does hand engineered features work? Because we know that in convolutional neural networks, they use something called as convolution filters. So filters are important. It is just that humans do not define the filter values. It is learned in the process of deep learning. So it's learned during back propagation. So, but before that, what exactly is this filter doing to an image? If you had an image and if you had a filter, what exactly happens to this image? We should spend some time on that. So just keep in your mind the two types of systems. First one is rule-based, where in my case, I was manually meaning I was writing an algorithm which could measure the length and breadth of the grains. And then I was using that length and breadth to predict the category of that rice grain, right? But in deep learning, you won't do that. You are simply feeding the image to a deep neural network, and all the features that the neural network has to learn to make a prediction will be learned automatically. If the feature includes the color, that will be learned. If the feature includes the textures that is present in the rice grains, that will be learned, right? So features are there. The only thing is it is not hand engineered. It is automatically learned during the process of training. So this course, I would say 90% of this course will be dedicated to deep learning approaches in machine vision or in computer vision, because that is what is most sensible for us to do. So if you think of bunch of tasks which you may have seen people implement using computer vision approaches, the classification is the easiest one, right? I'm sure all of you have played a little bit with CNNs for MNIST image classification for handwritten images, or cat versus dog classification. So this is the easiest thing to do. How many of you have heard of this website called Teachable Machine? So this is by Google. So if you want to build a convolutional neural network, I mean, not build, you can upload images and you can build a CNN to make predictions here. So just to get a flavor of how the training works. So it has become such an easy task now that classifying images is not at all difficult, provided there is sufficient diversity in the data. But there might be tasks that you have seen, like object detection. What is this? You draw bounding rectangles, something like this. So classification would be something where you have an image, you are trying to classify the entire image into whether it's a cat or whether it's a dog. So like a two-class classification. But in object detection, you are not classifying just the image. You are trying to identify an object in the image, and you will draw like a bounding rectangle. And this bounding rectangle is characterized by its, I would say, this left-hand side top corner, its width and its height. So if you know those four parameters, x coordinate of this point, y coordinate of the point, width and height, you know where the rectangle is. And whatever is there in the rectangle, you can classify whether it's a cat or dog or whatever. So these are called object detection. Then there are other tasks, which is semantic segmentation. So semantic segmentation is not about drawing bounding rectangles. So if you were doing just object detection, you would draw a bounding rectangle around this person, right? And you will generally say that the person is found inside this bounding rectangle. But there are techniques such as UNet, which we will be discussing in today's in this bootcamp, where you can perform semantic segmentation, where the contours of the object itself is captured, not like just a bounding rectangle proposition. So these techniques we'll be learning because these are very industry relevant. Then there are techniques which can help you with tracking objects. So tracking objects means if you have a video, in the video, let's say you have a CCTV footage where people are walking. And if a person is walking, in one frame, the person is in one location. In another frame, the same person might have reached another location in the image. How do you know it is the same person? You have to somehow figure out a way to track that, okay, this person has an ID. So let's say ID of this person is 233. So you draw a bounding rectangle and that bounding rectangle has an ID. And then when the person walks and reaches another point, so let's say the person is now here after like 5 seconds, then the bounding rectangle will be again drawn here through object tracking. But somehow you have to be also, you should be able to assign the same ID. That's how you know that you have tracked the same person when the person walked from place A to place B. So these are techniques called object tracking, which we'll be see again in this course. There are techniques for counting objects. Counting meaning if you have a conveyor belt through which things are moving, then you can count how many objects pass through the frame. If you are having a CCTV camera in a traffic signal junction, then you can count the number of cars that have passed through. And this may help you devise traffic signals in such a way that roads that experience too much traffic should probably be given the green signal for more time. So when I go home from here in my office, usually the route I take has only 30 seconds of green signal, and then you have to wait for 150 seconds for you to pass through. On the other hand, if it's through the main road, the signal is on for around 120 seconds and you have to wait only for 30 seconds. So how do people come up with these decisions? Because these are numbers, right? You quantify certain things and you take certain decisions, and computer vision comes into picture in such applications. There are applications where you might want to estimate the pose of a human. So a human has a shape. There are nodes like this. There are edges like this. And you want to figure out how the person is moving, and you want to fit a posture or pose in real time to a person's movement. This might be helpful in sports, in martial arts, in many settings where fast, dynamic human movement is involved. And then there are classic computer vision techniques, which we will briefly discuss today, which will help you identify the outer edges of an object, the top edges of an object, the corner edges of an object, etc. And at the end of the day, in an industry, you have to implement whatever method you have to implement it in a pipeline. So this pipeline also we will learn how to build. And for that, we will be using a platform called RoboFlow. So this pipeline will consist of model, data set, model, training the model or using pre-trained model, and then deploying it so that it is real time, it's live on a website or on an application. So what all techniques are we going to cover in this bootcamp? Let me just scroll back up. So in today's lecture, our primary focus is OpenCV. OpenCV is by far the most popular computer vision library. If you are a person who is serious about computer vision, you must spend time on OpenCV. The second part of the bootcamp will be about RCNN, region CNN. So it's a technique for object detection. Then we will learn about UNet, which I showed you earlier for semantic segmentation of images. So contours can be extracted. And then I would say YOLO might be the most popular model among all these in today's world. So there is a very modern method called YOLO V8, using which you can perform very fast real-time object detection. And finally, we will see how many of these different models can be deployed for an actual real-life application in the RoboFlow platform. So that will be a very, and one more thing is, whenever we are implementing all these frameworks, we will obviously be using OpenCV there also, but we will initially have a brief introduction to OpenCV before we go into these different architectures. So each architecture I am splitting into two parts. In the first part, I'll be covering the theory. What exactly is this architecture? How did people come up with it? We will try to code it as much from scratch. We won't be coding entirely from scratch, but we will try to do it as much as possible. And then we will try to train a data set for a particular application. And that's how we'll get hands-on experience. So I want all of you to be able to code along with me during the lectures. And the setup required for that, I'll be explaining how to do it today in today's lecture. So this is the rough outline of what we will be covering in this bootcamp, right? So here are some logistics in case you are not aware of. So we'll be meeting for 5 weeks. All the lectures will be live. We'll meet 2 times a week, first on Monday and next on Thursday. And the timing will be 2 to 3:30 p.m. IST. So that is about the lecture schedule. And there are 2 types of people in the program. There are people who are part of the free plan, people who are part of the pro plan. So for free people, the lecture videos and the basic code material, which we'll be discussing in the lecture, will be available. And the rest of the things will be available for the people who are enrolled in the pro, which will include GitHub repo, Discord community, certificate, a hands-on CV book, which we are currently writing as we speak, and all the other things, including handwritten notes, assignments, etc. So just check it out if anybody is interested. And with that, I think, yeah, one more thing which I wanted to mention, because in this month of August, we have actually 3 bootcamps running, and many people had asked, like, if they want to attend everything, what is the best idea? So we have thought of bundling this into one single thing. So there are 3 bootcamps. One is this hands-on computer vision. There is another bootcamp on reinforcement learning, which started last week. So it will be for 8 weeks, taught by Dr. Rajat from our team. And Dr. Raj is teaching build SLM from scratch, small language model from scratch, which starts from August 9th onwards, which is this Friday, I guess, right? Friday, sorry, this Saturday. So just check it out. There is a 3-in-1 bootcamp link. You might want to see if this is something that you are interested in or not. So I will share the link to this website here in the chat. So Jayadeep has asked a question. What about a DTR method? So basically, we'll not be covering transformer-based approaches in the current bootcamp. That is not part of the agenda. Although I would like to teach vision transformers and other attention mechanism-based approaches, which also involves techniques like unit embedded in it. But that I don't think that will be within the scope of the current bootcamp. All right. So now that being said, what all have you heard of computer vision? Whatever it is, in general, I can make a blanket statement that whatever we have heard is just the tip of the iceberg in computer vision, because usually we are exposed to solutions for customer facing problems or computer vision implemented in customer facing applications. So what is a customer facing application? Maybe you may have seen of some KYC, know your customer thing done automatically using some face recognition. You may have seen Digiyatra, which still does not work very well, but in many airports, it's getting implemented. It has computer vision embedded in it. You have your maybe iPhone unlock feature, which again includes computer vision. But these are applications where you as a customer is directly getting exposed to. And what you see as a customer is, I would say, a very, very small fraction of all the industrial applications that is out there for computer vision. There are many things happening in the backend, which most likely we will never get exposed to in the computer vision domain, right? So I just wanted to lay this out there just so that you are aware of the fact that there are many other applications. Now, these are some domains in which you can, in some of these applications, you are finding it easy to imagine how computer vision is coming to picture. So if you think of healthcare, I know personally know some companies who are building simple solutions for robotic assisted surgery, where the robot is primarily guided. I mean, it has a lot of sensors and probes, but at the end of the day, vision systems are one of the major part of these robotic surgical systems. Self-driving cars, needless to say, you're already aware of this. But then there are many other applications, like in manufacturing processes. If there are computer vision applications going on, you will never get exposed to it because you will only get exposed to the final product. You will have no idea what people are doing using computer vision, quality control, or inspecting the assembly line, what's happening in the assembly line, etc. In fact, 2 of my friends are running 2 separate companies. One company is in the physical security space, another company is in the industrial automation space. Both of them are heavily using computer vision systems. So one is for CCTV surveillance in airports, in general public spaces, or even private spaces. Let's say you are running a business, a physical center, or a store, like a grocery store. How would you ensure physical safety? What kind of computer vision systems can you implement to alert you of any security threats that's happening? So one of the projects that we are going to implement today in today's lecture is like a burglar detection system. We will code it from scratch using OpenCV. We will not be even using any complex deep learning techniques yet, but you will see how beautifully it works. So we will get to that in the last part of today's lecture. But there are countless number of applications. There is one of another friend of mine who's running an agricultural technology company. And in that company, what they're trying to do is they're quantifying how much pesticide, when you are spraying pesticide, how much of it is actually ending up on the plant. Because if you won't quantify that, the problem is you will almost always end up overspraying. And what happens to this oversprayed chemicals? It will, at the end of the day, it will reach inside your body or inside some animal's body, which is not good for you or the environment. So there are computer vision applications in almost every domain. You may have heard of this company called Blue River Technologies. So this is a company based in the US, and they got acquired for almost $300 million or something by another big agricultural equipment company. And what they were doing was they had a thing for, they have these sprayers, right? So there are so many mini sprayers equipped by cameras, and these cameras were activated. I mean, these sprayers were activated only if a crop with weed is detected. Otherwise, it won't be spraying. So this was tested on a specific type of crop, I think lettuce or something, lettuce or cabbage or something. And then they showed the proof of concept of how it works. And yeah, I think they were acquired by John Deere, this company, which is like I think they're $100 billion company. So there are many such applications. So as a customer, you are just eating the food, but before the food reaches your plate, it has already gone through a bunch of computer vision applications. Last year, I think this was in 2024 or early 2025. I forgot the timeline, but you might have seen this back and forth happening between Jan LeCun and Elon Musk. So Elon was saying, we don't use CNNs, to be honest, these days in their fully self-driving. So FSD means fully self-driving cars. But then Jan was asking, okay, if you don't use convolutional neural network, how exactly are you saying your real-time camera processing works in self-driving cars? So this was an interesting series of tweets you could follow. And of course, this was the same time when terms like vision transformer became popular in the, not in the scientific community, but among the general public to some extent. So we'll start the lecture with OpenCV. But before that, I want to show you one video, just in case any of you haven't watched this.
So I'm currently in Los Angeles. Actually got invited out here by...
Can you see the video? Can you just, I just made it full screen. Just wanted to ensure that you guys can see the video. Okay, sure.
Waymo to come.
So I'll just show you. So this is Waymo, another big company. So basically it works like Uber, right? So you have an app, you call the taxi and taxi arrives, and this has no driver. This is actually there in Chicago and various other parts of the US. So one of my friends who recently went for a conference there, he actually went in a Waymo taxi. There is actually no driver. It's crazy. Like it feels like we are living in the future. Although this has been coming, like for the past 10 years, we have been hearing fully self-driving car, self-driving taxi, self-driving buses, but now it has become a reality in many parts of the world. And although while watching this in a video, it doesn't feel as amazing, but I can only imagine the excitement of the person who is actually sitting inside that feeling. And it can go pretty fast. It's very cool. It can go pretty fast. So, and how does this work? Of course, computer vision. I don't know what models they use. So I have spent a lot of time trying to exactly understand what all models do Tesla self-driving cars use. Most of it is proprietary, but they don't use one single model. They have a plethora of models for different tasks. So for object detection, they have one type of models. For classification, they have some other model. But these are still the tip of what is actually happening inside their algorithm. I don't think we'll never know what exactly happens. But one claim that Elon Musk has made, I think, is they also use vision transformer, right? So if vision transformer is being used, as Aravind is mentioning, it can have a mixture of experts instead of mixture of experts for text, mixture of experts for vision. And these cars are apparently safer than human drivers. They have tested it over many 100,000 plus kilometers, and then they have made only very little safety incidents. All right, so now let us get into the main part of today's lecture, which is OpenCV. So with this, we can get to our work. So OpenCV is a Python library mainly meant for processing images or videos, because videos are ultimately collection of frames. So we will spend our first two lectures, so today's lecture and next lecture, purely on OpenCV. Every single one of you will 100% sure end up using OpenCV, right? So this is what was happening in the scene of computer vision, as I mentioned earlier. Before roughly around 2010, people were using hand-engineered filters. So what is hand-engineered filters? It will look like a bunch of matrices. This is an example of a hand-engineered filter. You have a 3x3 matrix, and you have some numbers inside this matrix. And this matrix performs convolution operation on top of the images. And this will result in a output image, which may capture some features from the image. So for example, I have a picture, not this, but this is actually a picture of a girl with a hat. And if you apply a certain type of filter, see, it detects just the edges, the places where sudden transition in pixel values happening. So these are classical filters that are hand engineered. But then, as I mentioned, AlexNet in 2012 changed the entire scene. I don't expect you to understand how AlexNet works or even the architecture. That's not the point of this bootcamp. But just remember the name AlexNet. Just remember the year 2012, because it really marks a division between classical computer vision and deep learning guided computer vision. Now, let's spend a few minutes on these filters, right? And we will try to implement. So let's say this is your input image. And this input image is represented by pixel values. Let's say it's 0 and 1. So white pixels are 1s, black pixels are 0. So the pixel representation of this input image would look something like this, right? Now, if let's say you want to apply an edge detection filter, what does that mean? Where is the edge? First of all, the edge is here. This is the edge. And if you want to detect an edge, if you want to detect this edge, you are essentially applying a filter where you are seeing when the pixel values are changing from 1 to 0, 1 to 0, 1 to 0, right? So this is what you want to get. So if you apply some filter to the image, it will only highlight the edges. Everything else that is not an edge will not be highlighted. What does that mean? Everything that is not an edge will be black in color, as you see in this region, black color, this region, black color, and whatever is an edge will be highlighted in white color. And this may be represented like this. All the pixels in the exact middle are in values of 1. All the other pixels are of value 0. Now, how can you accomplish this? Let's see. So let's say we are using a filter like this: 0, -1, 0, -1, 4, -1, 0, -1, 0. So this is how you apply the filter. So I'm going to write it here: 0, -1, 0, -1, 4, -1, 0, -1, 0. Okay, so this is being applied. So the way it works is, you will, let's say the filter is overlapping with this set of 9 pixels. You will do 0 multiplied by 0 plus 0 multiplied by -1 plus 0 multiplied by 0 plus, like that you will do. And the resulting number, whatever that is, will be assigned to this pixel, this center pixel. So here, what will be the resulting number if you perform this operation? So if I perform this filter operation to this subset of images in the input image, the result will be 0, right? So here it will be 0. So this is the output image, by the way. The input was this. So I was supposed to write here, but here also, if the filter is, let me just bring the filter up here. Okay, so here what will be the output? The output is assigned to this center pixel, but what will that be? That will be 0 again, because whenever there is a 1, those are getting multiplied by -1, and those -1s are getting added up 4 times, right? And then -4 you will get, but then that is getting cancelled with this +4. So the pixel value of the output corresponding to this will be 0. So you are supposed to get 0, because output should be something that looks like this. But let's say my filter is somewhere here, over here. What would be the output? The output will be assigned here. And let's say I'm applying the filter and taking absolute value for simplicity. What would be the output? Let's take absolute value for simplicity. It'll be 1, right? And 1 will be assigned here. What if my filter is over here? What would be the output if my filter is here? Oh, sorry, I have selected 9 plus 3, 12, but let's say these 9. The output will be 4 minus 1 minus 1 minus 1. Again, it will be 1. So what this shows is if somehow I can have a filter that follows a certain logic, then I can use this filter to extract some relevant information from this from our image. Okay. Now what I'm going to do is let's all design a hand engineered filter. Instead of writing it mathematically, we will open a website. So I will share the link to this website in the chat. So just go to this website. Okay. And I will also share an image with you, which you can play with. So the image that we are going to use is this one. All right. So please use this image. And what we will do is go to the website, scroll down. In this section, you will see this choose file option. So here, choose the file and upload the image which you just took the screenshot of. Okay, so that image will appear here. All right. Now what I'm going to do is I will apply a filter which will detect just the top left edges. So top left edges means these edges. Okay. And I will use a certain logic. I will tell you the logic later, but I'm going to enter certain numbers here and you will see that the top left edges are getting highlighted. See, the top left edges got highlighted. So here I hand engineered a filter for this. Now let's say I want a filter for just identifying the bottom edges, no other edges, just the bottom edges. Then I will do something like this. See, now only the bottom edges. So here there is actually a very interesting logic which you can follow. Okay, so let me go back to the original configuration. So the original was, I guess, the original was something like this, right? Now imagine that these shapes are protruding outside. So this circle, square, triangle, diamond, those shapes are protruding outside the screen as solid objects. And imagine that there are light rays going from one location to another. The light rays should go from bottom to top if you want to illuminate the bottom edges. The light rays should go from top to bottom if you want to illuminate the top edges because they are protruding. Now consider negative numbers in the filter to be source of light ray and positive numbers to be destination. So basically imagine that light rays are going from negative numbers to positive numbers. Then your filter, let's say you want to detect the top edges, your filter should be designed in such a way that negative numbers are in general at the top. So at the top row, I will put -1, -1, -1. Middle row, I'll just put zeros. And the bottom row is 1, 1, 1. Then see, top edges are getting illuminated. So negative numbers are at the top, positive numbers are at the bottom. It's as if the light rays are going from top to bottom. And these light rays are now illuminating the object at the top edge, these protruding objects. It's just an analogy. There is nothing like this. I just made it up, but it works. Now, if you want to illuminate all the 4 edges, right? Let's say not just the top edge, not just the bottom edge, then how should light rays come? By the same analogy. If you want to illuminate all the edges, what should the light ray look like? It should come from all the directions, correct? So you want light rays to come from all the 4 directions to the center. So center is now the destination of the light ray. So center, I'll put some positive number, let's say 4 plus 4. And I could maybe say the corners, I could maybe put 0. It's not a problem. But these 4 numbers, I'll put negative, -1, -1, -1, -1. Now you see all the edges are getting illuminated. If you want to increase the brightness, I think what we can do is just double the numbers. Then the contrast will be increased, enhanced. So see, so what did we do here? We defined a human logic for designing a filter for detecting certain features. If the features of interest are edges, all the edges, then we can design the filter accordingly. If we only want some corners, we can design it accordingly. And like this, there are dozens of filters that people have developed over many years before deep learning. for detecting different patterns in the objects. And this was classical computer vision. But it works. It works for many, many cases, right? Today, what we are going to do is we will use a classical computer vision approach for a similar task. So before that, OpenCV, please know that it has huge number of downloads per week. So apparently the numbers are close to or above 5 million per week. It's crazy number. So OpenCV is by far the most popular computer vision library. They even have a website. So just check it out, OpenCV, this one. So they have bunch of courses also. If you're interested, just check it out. It's a great platform. But that being said, our goal is figuring out how to use it, right? So you can use OpenCV for many different tasks, for reading images from camera, from your computer, annotating on the images like drawings, or you could run object detection algorithms. So you could have had a deep learning model that is trained elsewhere, but you could perform inference using OpenCV on your system. So we will implement those in the next lecture, but today let's focus on a few things. So today what we are going to do is we'll read an image, we'll try to read video, perform basic image processing, and then at the end of the lecture, let's build a burglar alarm system, which is if, let's say, you have a CCTV camera, it's a live feed and it's in the indoor, okay, inside your house. Now, how do you know if, assuming nobody is there in your house, how do you know if a burglar has entered the house? You will know that when the camera feed has changed. If some changes have happened, it's a signal that something has moved in your camera feed. It could be an animal, it could be a person, maybe some object has fallen down, it could be anything, but it's an anomaly. It's an anomalous incident which you have to notice. So by the same logic, we will be implementing a computer vision system using OpenCV. But before all of that, we have to install a few things, okay? So I will be using VS Code for coding. So all of you, I recommend you to install VS Code, but if you use Anaconda or any other platform, it will be good. Google Colab will have some issues with respect to allowing camera access. So I won't recommend Google Colab for this particular bootcamp. I would recommend ideally VS Code. So VS Code is like an interface for programming in various different languages, and you can install it here. So I'm sharing the link. So as I'm speaking, just download VS Code for your computer. And don't worry if you have never used this, it's not an issue, but please have it ready, okay? So this is the first tool. It's available for Mac, Windows, whatever. Now, what else? Okay, next is Python. So go to Python website, go here and download whatever is the latest version. So you can download from this link. So go to Python website and download it. Then the last thing will be installing OpenCV. But before installing OpenCV, you should have your setup ready. So preferably VS Code, and you should definitely have Python, okay? So assuming that you will be doing this on the side, let me tell you how to install the OpenCV library once you set up your Python installation and once you have VS Code ready. So we'll be creating a virtual environment. So a virtual environment is something where all the libraries or all the packages that you are installing for this particular project, it won't be installed globally on your entire computer. It will be installed in a local environment in which you can play with. So it's a very good practice. So what I do is go to VS Code, okay? I will start from scratch so that you guys can also follow. Click maybe and go to your folder wherever you are having your folder to be installed. So keep a folder called hands-on computer vision for this entire bootcamp, and in that create subfolders so that you have everything stored in a systematic way. And here I can press Ctrl+O to open any particular folder. So I have a folder which I had created last week called Computer Vision Hands-on Bootcamp, in which bunch of things are there, but you can ignore all of this. I'll start from scratch. So this is how I can open the folder. So go to any folder, create an empty folder there named Computer Vision Bootcamp, and then open it using VS Code. When you open it, here, if you click the file button, you should see ideally all the files that are there in the folder. For you, there will be no files because you have not added anything yet. For me, you can see that there are some folders and files. Oh, you can only see Miro board. Thanks for letting me know. Let me stop sharing and reshare it again. Okay, did you guys see this Python website and everything? All those part was okay, right? Only when we started VS Code, you did not see, correct? Okay, awesome. And do you see VS Code right now? Okay, thanks for letting me know. So I'll repeat once again. So open VS Code and go to your downloads or wherever you want, or desktop or wherever you want to keep your folder for this particular bootcamp. So let's say here I create a new folder called I can name it as CV Bootcamp. Okay, and then go to VS Code, Control Open, Control O, and then you can go to that folder, navigate to that CV Bootcamp and open it. And this will open the blank folder on your computer, on your VS Code. One more additional thing which I want to ask you to do, which will help you tremendously, is installing Copilot. So VS Code has this thing called extensions. So click this extension. So this icon is extensions. And here search Copilot. And this will help you install the GitHub Copilot, which is like an AI coding assistant. Although we won't be using it extensively in the course, because here our purpose is learning, not just implementing. So we will try to not use it as much as possible. But when you are actually building your CV systems, when you have a Copilot, it will be very helpful. So I'll show you how this helps. So I have installed Copilot already. It's already activated in my computer, right? So now let's say I have this folder opened. Let me open my computer vision folder. Okay, so and here I just create a test.py. Okay. And my Copilot, you see this icon, that's the Copilot icon. I can just go here and then whatever code I want to, let's say here I'll say, write a hello world. Oh, there is actually one more level of automation which you can do. So I use this software called Whisper Flow. I'll show you the website, PR Flow. So this is like a speech to text software and it's amazing. I'll show you how I usually use it. So if this is my VS Code here, I'm not typing, okay. I'm just pressing the function button on my keyboard I'll just say, write a simple code for writing hello world in Python and execute it. So I just said it and it converted into text to speech. So this is how you can do a lot of vibe coding. But anyways, do it with caution. So here what happens is this Copilot will write the code. So this is very similar to Cursor, right? You might have heard of Cursor for programming in like vibe coding. So this is pretty much the same. And here, if you want to implement this into your code, you just need to click this button. Then it will come here, like it's in your code. Or if you want to make changes, you can just say that. If you are encountering error, you can use it. So it's basically like using ChatGPT only, except here you are having it embedded into your IDE. And here you can see that there is GPT-4o. There are different models available for you to choose. So my default model is Cloud Sonnet 4. Anyways, I don't want to spend too much time on this, but I thought I will just let you know that such an option exists in case in future you're kind of bored with coding by hand. Okay, now let's come back to our main thing, which is installing OpenCV. So all you need to do is, this is the, or before installing OpenCV, we have to create a virtual environment, right? So this is the code for creating virtual environment. I'm just pasting it. Basically, this will create a, I would say, a localized space where you can install your libraries and run your code. So my virtual environment name is hands-on-CV. So you can choose whatever. This is the name of the virtual environment, the hands_on_CV. You can put whatever name you wish to. Yes, you will have access to the recording. anyone who is wondering about that. And here, this line will activate that virtual environment. So you create a virtual environment and you activate it. And how do you know if your virtual environment is active? So here you see, I have this in the bracket, I have hands_on_CV. That is the name of my virtual environment, and it is active. So this is how I know that my virtual environment is active. Now, once this is ready, you are now ready to install OpenCV. And this is the code for installing OpenCV. Pip install OpenCV-Python. So pip is like a package manager for Python. So whenever you are installing new packages, new Python libraries, you will use pip. So just use this code, pip install OpenCV Python. This should hopefully install OpenCV. I don't think you will encounter any error. Now, let's do some basic operations. Okay. So first we will do a little bit of image reading, image processing. We will try to annotate on a particular canvas. We will try to draw rectangles, etc. And then we will move on to accessing the camera feed or accessing the video, like a video on your computer. And then you will be able to implement a code for detecting burglar presence in your video. So we will build this entire project together in today's lecture. So, but before going into the project, I want to spend a little bit of time on OpenCV basics. Okay, so just open a new file. Can anyone mention in the chat if you guys are ready with your Python and VS Code? Yeah. So everybody will get access to the recording, so don't worry about that. Okay, so you guys are ready with VS Code and OpenCV. Did you install OpenCV? Okay, still installing. One error some of you might encounter while running some of the projects, not these ones, later, will be, it might show that NumPy is not installed. Usually NumPy is available, usually NumPy is already there on the computer, because if you have run basic Python projects, you might have already used NumPy. If you encounter that error, it's most likely because you have to downgrade the NumPy. So once we reach that stage, just remind me, like if you ever face the issue of NumPy not found or something like that, just let me know in the chat. But today, I don't think you will face that issue. And feel free to help others, like, because I'll be coding here on the side, but if your fellow classmates are encountering any issue in installing, just feel free to respond to them to help them. But here, let me open a new file. So I will say this file could be read under, or maybe I'll create a new folder called lecture 1. Inside this folder, I'll create a file, read_image.py. Okay. And then if you want to import OpenCV, this is what you can do. Import CV2. So this will import OpenCV. Of course, you have to have OpenCV installed first. And then for reading, you use cv2.imread of whatever is your file name. Okay, so whatever is your image name, .jpg or jpg, whatever it is, you have to write it here. So in my folder, in my present working directory, so if you want to know what is your present working directory, type pwd here. You will see the present working directory. My present working directory is computer vision hands-on bootcamp, which is this entire folder itself. So here I have a file called sridhar.jpeg. So all I can do is here I can put my file name sridhar.jpeg. And if I run the code, I have to assign also. So I will say img1 image1 equal to cv2.imread of sridhar.jpeg. Now, if I run this image will be read. Okay. Now, next step is the red image has to be displayed. So cv2.imshow of, and then here we can give some name to the displayed image, the original image. And then here we are displaying the image that we just read, which is img1. So here we will display, using imshow, we will display the red image. And one more thing is cv2 dot wait key of 0 for closing the image. So let me do one thing. Let me first of all close a bunch of these things and start from scratch. So see, this is the original image. So we just read an image from our file. The original image had a file name. Then we are providing a title and then we are just displaying it. And here, if we press escape key, the image will close. So I'll share the code here. So just check it out. Now, a simple thing which we can do is cv2.imWrite, which is writing an image. So we can save this image which we have opened as such, or we can modify and save, we can crop and save, we can annotate and save. But basically, at the end of the day, we can save it back into our computer with the name saved image, let's say saved underscore original underscore image.jpg. And what are we saying? Saving, we are saving this img1. Okay. So if I run this now, you should see a new file appearing here with this name, saved underscore original underscore image. So see this one. Where is my saved image? Yeah, saved underscore original underscore image. So basically we did the following. We opened an image, we just displayed an image and we saved it. Very basic operation, nothing fancy. So I don't want to spend too much time on this. Next is we can perform a little bit of processing of these images. So let me create a new file, which is named as image underscore processing.py. So here we will be opening an image and we will perform certain operations. So import cv2 for OpenCV, and then we will read the same image, img equal to cv2.read .imread of sridhar.jpg, and use whatever file name is there for you. Then what we can do is let's perform some operation, resizing, and then grayscale. Then we could do blurring. Then we could also do something like edge detection. That's it. So we want to do these following operations on the red image, and we want to maybe display those images. We don't want to save it. So resizing can be done like this, cv2.resize. So here, this cv2.resize will resize the image into a 640, 480 pixel image. Okay. And gray will be cv2.convert color. So cvt color of. So we are converting the color of the resized image. So we can convert the color of the resized image, or we can convert the color of the original image. So here I'll convert the color of the original image. So we are converting the color of original image. And what are we converting it to? We are doing color underscore BGR to gray. So BGR is same as RGB, but this image is following a different convention. It's not RGB format, it's BGR format. Then blurring equal to, let me just delete this automatic fill. cv2.Gaussian blur. And in Gaussian blur, I want to use the original image only. So img, comma, and now the blurring happens again using a filter. So you saw the filter for detecting edges. Here, blurring also can be done using a filter. So here we could use 5x5 filter. Actually, you know what? Let me use 2x2 filter first. And then let's display what it looks like. Then there is an edge detector called canny edge detector. It's also a certain algorithm which involves usage of a specific type of filter. So cv2.canny. So canny edge detector is actually very, very famous. We will be using it on img and 100, 200. Now let's try to display this cv2.imshow of all of these, right? So we have to show the resized image, we have to show the grayscale image, blurred image, we have to show the edges, and then we'll add a wait key for basically exiting. So exiting meaning we want to quit the image window and then destroy all windows. So this is not needed. Okay, so now if we run the code, hopefully it should show you the processed images. Let's see. Okay, I think let me go back to 5,5 and then let's see if it works. Yeah. So this is the edge detector. So canny edge detector worked. This is the blurred one. This is the grayscale image, and this is the resized image for 640 comma something, right? 480 or something. So now let us close this. Now what will happen if I change this to 15 comma 15? What do you think will happen? In the blurring, I just changed 15 comma, change it to 15 comma 15. It should ideally become an even more blurred image. You see, it's even more blurred now because now we are using a bigger filter. Similarly, we can do something like, so canny, I think somebody has asked a question, what is this 100 comma 200? I think it is something like this. You want to define a bounds for the pixel values. So I might be wrong, just do check this one. 100 comma 200 is the lower pixel bound and upper pixel bound, I guess. I forgot what it meant. Now, in the Gaussian blur, what if we keep this as 50 comma 50? Right? We can play with canny edge detector values also, then we will see. If this is 50 comma 50, then we will have extreme blurring, but here I'm facing some issue. Maybe let me go back. Okay. So can anyone mention in the chat, how far along are you? Have you been able to implement some of this? I'll paste the code here. Have you been able to implement at least the first part of the code? Okay. Now let me run the code. Okay, so now let's play with canny edge detector. So I don't want to display these. Let's just do canny. So here I will say 0 and maybe 255, and let's see what happens. Then we can understand what the numbers are doing. All right, so here we go. So this is the canny edge detector with 0, 255. What if this was 0, 0? Yeah, so when this was 0, 0, it is detecting far too many edges. I guess, is it because are we reducing the threshold for what should be an edge? Something like that. Let me go to 255, 255. So when it is 255, 255, it's only detecting the absolute sure shot edges. When it is 0, 0, it is pretty much detecting all the edges. And when it is 100, 200, it's detecting something in between. Actually, you know what? Let's ask our copilot. In canny, what happens if the arguments are 0, 0? Yeah, so all pixels will essentially become edges, loss of edge selectivity. So lower threshold. So yeah, so lower threshold is 0, upper threshold is 0. So I think it was not the threshold for pixel values. It was the threshold for gradient, I guess. So if there is a sharp gradient, how sharp the gradient should be. I think this 100 is a measure of the minimum sharpness of the gradient. 200 is the measure of maximum sharpness of the gradient. And how is a gradient defined? Gradient is the change in pixel values happening from one pixel to the next. Okay, so basic pixel manipulation, right? That was what this is. Now, let us do one more thing. We will implement a burglar alarm. Actually, before that, let me show you how to implement drawing or annotating on an image. So I'll create a new file called annotation.py. Okay. And annotation simply means we are drawing some shapes. You might have seen object detection almost always involves drawing rectangles on top of images. Rectangles are superimposed. So import CV2. Then here you will need NumPy. So import NumPy as NP. So if you don't have NumPy on your computer, just say pip install NumPy, I guess. Then we have to define a canvas. So canvas equal to numpy.0. So it'll be like black canvas. You define the size of the canvas. It could be 512 by 512, comma 3. So you have all the colors, comma data type equal to np.unsigned integer. So this will define a canvas in which we can draw. What can we draw? We can draw many things. We can draw shapes. We can put text. So we'll be using all of this in the burglar alarm detection. So we'll be using there how to read an image, how to annotate an image, and how to detect changes happening from in the pixel cluster from one frame to another. So here, actually, this code that I have in the recommendation is already looking perfect. Rectangle canvas, it has the 100, 100, 400, 400. Yeah, that looks fine. So CV2, we can start maybe with a line itself. So line is, we are drawing it on the canvas. And let's first display this. So CV2.imshow, and we will say canvas with shapes. And what are we displaying? We are displaying canvas. So first let's see this, but we have to add the wait key and destroy all windows. The reason why we add these two lines is so that we have a key press available for closing the canvas. So when we run this, hopefully we should see a canvas with black color in which a line is there. And the line, I guess, should be red color. Let me see, where is my canvas? It is BGR, not RGB. So BGR. So if I keep this as 255 and this is 0, I guess the line should be green now. Where is my line? Yeah, so this is my new line. So this defines the starting point of the line. This is the ending point of the line. This is the color of the line, and this is the thickness of the line. So if I make this 15, you will see a giant line. Let me run this. Very thick line, right? So this is the characteristic of the shape. We could do now a rectangle. So CV2.rectangle. Where are we drawing? We are drawing it in the canvas. And this is one of the vertex, the diagonal vertex, the color. So BGR. So this rectangle will be 255. And that's it. So we have a rectangle and we have a green line. Now we could also put a text. So this rectangle is very useful because we'll be putting rectangle, bounding rectangle around shapes. Then CV2 dot, I would say, put text of canvas, comma, we could say something like OpenCV text addition. And we want to define a place where this text is added. And font, I don't care about the font. So 10, let's say 500. Let's see without adding the font what happens. Maybe some default thing will happen. Okay, I guess font is needed. So, comma cv2 dot font Hershey simplex, some random font that was in my recommendation. So now if we run this, it will use this font. I think one of them is the font thickness, and this is the color. So font color now should be white because it's BGR 255, 255, 255. So the text should be white. See, OpenCV text addition. So this is how you manipulate canvas. Now the canvas could be anything. Canvas could have another image on top on the background. So it will look as if you are now drawing pictures on top of the image, right? So I will share this link, I mean, this code also in the chat. Just let me know if you are able to run all of this. 1 second. Yeah, just let me know if you have been able to run some code, because now the whatever we are going to run right now is the most important one. So I want all of you to be able to run this. I think it's to mention the pixel values. So in NumPy, you can add floating point numbers. You can add any type of numbers, but here in the canvas, you can't have a pixel value of 1.5. You have pixel values ranging from 0 to 255. So here I can, let's say I avoid this. I don't know if by default it will be integer or not. So let's see. I am removing the data type. Okay, now it is working. But what if it's a floating point? Float 64. How about this? Maybe, I'm not sure. Oh, this also works, surprisingly. Maybe somehow it is converting the numbers into integer by default, like it is rounding it off or something. But usually it is a better practice to ensure that the number that is in the canvas is a whole number, like a integer which is positive. Here you are starting with np.zeros. So you don't want 0.0, you want 0. Now what else? That's it. Let's now start with the burglar alarm detection code. So start a new file, not burglar alarm, burglar presence .py. Okay, so this we will start from completely from scratch. Now here is where you will be using both. You will be accessing camera on your computer using OpenCV, and you will access the camera feed. And you will also do one more example where you are uploading a video file, MP4 file, and then from that you will annotate whenever there is a moving object. So as usual, import CV2. You are importing computer vision OpenCV library. Then you say capture equal to cv2.video capture of 0. So you know what this will do? This will ensure that you are capturing the real-time camera feed. So video capture of 0 means you are capturing the camera feed. Cap means you are saving that whatever is being captured into this variable. Okay. Now what we will do is we want frames. For saving the frames, we are having an empty array. Then what I want to do is the following, right? The logic of burglar detection is this, a simple logic. I will first capture the frames from a video. Can you see the mirror board? Can anyone confirm if you can see the mirror board? Okay, thank you. So what we are going to do is either from camera or from a video, we will capture the frames. Now, when do you think in an indoor setting, when the house owner is not available at the home, and if nobody is there in the home, if there is an indoor CCTV, when is there a suspicious activity happening? Whenever somebody is moving, whenever something is moving in the screen, right? So for that, all we need to do is find the difference between two adjacent frames. Because if there is a burglar inside the house, in the CCTV feed, burglar will be moving somewhere, right? So initially in the current frame, maybe burglar is here. And after that, the burglar has reached here. So when you look at the difference between the frames, in the first frame, you will see a person here. In the next frame or after 5 frames, you will see a person here. So if you take the difference between those two frames, if you pixel by pixel, if you subtract, you will see that there is some difference. Rest of the things will be same, because if there are static objects in the frame, if there is like a wall painting, that wall painting there will be there in both paintings. So you are specifically targeting moving objects here, right? So first we define an array for storing the frames, and then we say gap equal to 5. So this we can say is for defining, okay, are you going to look at the difference between every adjacent frames, or are you only going to look at frames, one frame and then the 5th frame, then the 10th frame, so that significant changes can be detected? So I'll say gap equal to 5, and then count equal to 0, like frame count. So we'll start with 0. Okay. Now what we want is, we want a continuous camera feed to happen. So if we have a real-time camera, which I can show using webcam, I want it to run constantly. So then I will do this while true, so that this while loop will by default execute many times, unless we say otherwise. A value that is returned, comma, the frame that is returned, equal to capture dot read. So this, what this is doing is, you are defining the captured video in this variable called cap. Then from the variable cap, you are reading whatever is there in that frame. So the read things will be there in this frame, and whether something has been read or not will be there as a binary in this return variable. Now, if nothing is returned, so if not returned, so if return is false, which means then if not return will be a true condition, then you have to break out of that loop. Then you say just break. Break meaning you are not seeing anything in your camera feed, like nothing is coming into this cap variable. So you're going to return out of, you're going to move out of the yeah, this logic, exactly. So Shivam has mentioned this logic will identify cats and dogs also as burglar. Exactly, this will. So here we are taking a very simple logic where nothing is expected to move in the home. If there is anything moving significantly in the home, we will detect it as an anomaly, right? So that is the logic that we are implementing here. Now, but if this is not true, meaning the return thing is not false, then what we will do is the frames that we have captured, so gray equal to CV2 dot convert color of frame. So we are converting whatever frame we have captured into a grayscale image. So gray, I'm using a variable called gray, where I'm converting the frame using CV2 dot color BGR to gray, and I'm using this CV2 dot CVT color, which is convert color. Then I will append it to this empty variable. So I had an empty variable called frames. So frames dot append of gray. So the grayscale image, which is the grayscale version of my current frame, is now appended to the frames variable. Now, what I want to do is, I just want to check if the length of this, so after you append, right, I just want to measure once in every 5 frames. I mean, between frame 1 and frame 6, there are 5 frames. So I want to find the difference between frame 6 and frame 1. Then I want to find the difference between frame 11 and frame 6. Then I want to find the difference between frame 16 and 11, and so on. So I don't want to look at more than 6 consecutive frames at a time. So if count, I have to increase the count also somewhere, which I will do. But if, let's say, length of frames is greater than gap, gap is 5, so gap plus 1. So if my if the length of frames, which is this empty array, has now, let's say, 6 images, that is when I have to implement my logic. Then I will do frames dot pop of 0. So what does this mean? Gap is 5 and gap plus 1 is 6. If the length of my frames is 7, so let me draw an array here. I have an array for storing the frames. Okay, so I'll start my frame number from 0. So I have frame number 0. I'm appending frame number 1, number 2, number 3, etc. up to number 5. So once I reach frame number 5 here, now the total number, my length of frames is 6 here. Okay. Now if I append frame number 6, which is technically the 7th frame, then I don't need this anymore because I am calculating the difference between 6 and 1. So I don't need this, the 0th one anymore. So then I can remove this. I can just pop this. So this pop operation basically pops whichever is the first element in my array whenever the length of the frames array is greater than 6, meaning equal to 7. So then it will be popping the useless one, which is the first one. Now, if yeah, I can also add some text. So cv2.put text, and I could add like a frame number. So cv2.put text. So inside the frame, I am adding a frame count, and it is equal to the variable value count. So count is starting from 0. So I will start with frame number 0, frame number 1, and so on. And what I'm saying is cv2.put text inside the frame. I'm going to put this text. And why do I have this f inside double quotes? Because it's like a dynamic string. It's not a fixed static string. Then I have the color, I have the font, etc. I have the location where I'm putting the text, etc. So cv2.put text, I'm putting it at certain location and for certain color. So color will be BGR. So it will be green color in this particular example. Then what should I do? If length of frames is greater than gap, and what is gap? Gap is 5. So if the length of frames is equal to 6, basically, because greater than gap means greater than 5, which is 6. So if the length of the frame has reached 6, then what I will do is I will calculate the difference between two consecutive frames. So cv2 dot absolute difference. So abs diff is the function for absolute difference. And I will calculate the difference between frame number 0 and frame number -1. Can anyone tell me what is this -1, frame number -1? Exactly. So 0th element is technically the initial element. -1th element is you are circularly going back to the last index. So last item in the list. And absolute difference, because we only care about the difference. We don't care whether the difference is positive or negative. So we are taking absolute value of the difference. Then we will say we are using a thresholding, and we will say we are thresholding whatever is the difference such that all pixels with value less than 30 will be eliminated. So which means if the difference is very high, it means those regions will be bright, and you are only picking regions with certain brightness or above, because in the image maybe there is a flickering tube light. You don't want that flickering to affect your moving object detection. You ideally want only major changes happening, which means you're looking at higher values of pixels in your difference between frame 0 and frame -1, which is frame 0 and last frame. So if the difference is greater than 30 and less than 255, 255 is anyway the maximum value, you are thresholding that. So you are only selecting that. Then you will say this threshold is passed into a function for finding the contours. So contours equal to this will be contours equal to, or contours comma, there is also one more argument, cv2 dot find contours, and you are finding the contours in this thresholded image. So you will find it in thresholded in thresh, and cv2 dot, so for finding, so contour is nothing but where are the clusters of pixels that are happening, that are experiencing maximum value of change. So you are now finding those contours. Yeah, I'm getting suggestions while doing code because I have installed Copilot, I think, but there is also a native one for VS Code, I guess. But I'm not sure which one is giving me the suggestion, but I'm definitely having Copilot. If I switch this off, perhaps this will not come. But do install it, okay? Yeah. So contour is, imagine that you have a collection of pixels. So here, for example, in this image, the difference would look something like this. Let's say in my image, a person moved from here to the immediate next location. Let me just. Okay, let's say the person moved here. So then the bunch of white pixels that I will get in my difference will be over here. So pixels around this general region will be kind of white. However, if some small leaf also moved somewhere here, let's say there is a small leaf that is moving, there also I will see a collection of pixels. Then if I have some other small changes happening elsewhere, there will be a collection of pixels that are white. Now, what is a contour? A contour is nothing but this big group of pixels is now determined by, okay, let me just draw it using pen. This big group of pixels is now determined by this contour. There is another small group of pixels defined by this contour. This is another small group of pixels defined by this contour. Now, all these contours have certain size or certain area. And I only want to consider contours that are big enough. Meaning, if the contours have certain minimum area or above, I will consider those. Rest of the contours I don't care about, because maybe in the image some small thing has moved. I don't care about that. I only care about major things moving, because a burglar will definitely move, right? So maybe contour sizing threshold is one way in which we can eliminate a cat moving in the video, because a cat is a small animal. There are many methods, but I'm just showing you the most primitive way in which you can implement a basic logic, right? Now we will say, now that we have got the contour, for C in contours, so you are getting every individual item in contour. I'm sorry, I just pressed the tab for accepting the suggestion, but let me just put it from start. Then CV2 dot contour area of C. So you are picking each individual contour in the contours variable. Then if the individual area of that contour is less than 500, then you ignore it, because then this 500 is also like a experimental number that I came up with. I noticed that in sometimes for some type of videos, 200 is a better number. For some types of videos, 1000 is a better number. So we will play with this number, but basically this will eliminate those contours which are too small. So if the contour area is too small, it means it's a region where some minor changes happen, which you can ignore. So that is why you have continue here. Otherwise, you draw a bounding rectangle around the contour. And what would that look like? It will look like this. So I hope you can see the Miro board, but basically the bounding rectangle around the contour will look like this. It will look like this. It will look like this, but only for those contours which are big enough, not for all the contours. Okay. So now, if the contour is big enough, if it's greater than 500, then I have X coordinate, Y coordinate, width and height. X and Y coordinate of what? I just need 4 numbers to define a bounding rectangle. I just need the X coordinate and Y coordinate of this point. Then if I have that with the width and with the height, I can find the rest of the coordinates. So a bounding rectangle is defined by just 4 numbers, X, Y, width, height. Then what I will do is I identified the contours, and now I will say one more thing is I want to identify the motion. Like I need a binary variable for motion. So if I have motion variable like this, motion, any of CV2 dot contour area. So in the contour area, if in the CV2 area for individual, if any area is 500, then has it. So here what I'm going to do is contour area greater than 500. So within the contours, every individual C, check if at all for any of the C's, the contour area is greater than 500. If for one C condition is means at least one contour which has an area greater than 500 in that particular frame, which means in that particular frame, you have detected the motion. So motion will be true. If this condition is not there, which means there is no change that has happened in the contour, then this will be false. Then what we can say is if motion has happened and, so it's an and condition. So if motion has happened and let me not put the count variable now, just let me put if motion has happened, then I will say cv2.put text. I will put something like this, motion detected in the image and some font values. So this is the font family, the font color, etc., which we can change later. And I should also do one thing. Other than putting text, I should save the image. So it will be great if I have a CCTV footage, but instead of going through the entire, I went for a vacation for 3 months and then I'm back, or whenever I want to check a CCTV footage, it'll be great to just see the anomalies, right? Just the anomalies happening in the image. So I can save cv2.imWrite. I'm writing the image saying f motion frame count. So the count variable is counting the frame count. Then I'm saving it, and that's it, right? Yeah, and I can print also. Print that this thing is saved, and then I can show cv2.imShow. I'm displaying the image. Motion detection frame, and then count plus plus or count plus equal to 1. Then, yeah, I need to exit somehow. So if cv2.wait key, then I'll exit. Otherwise, I'll continue and then release the capture, destroy the windows. That's it. So first, let me run the code and show you what is this doing exactly. So I hope my camera will be visible, although it is being used in Zoom. So can anyone tell me if my camera is visible to you? Let me quit this first. That camera in which the green rectangles are coming, it's visible, right? Okay, awesome. So let me just delete all of this because there is too much things here. Okay, motion frame. So I should save the frame only if motion has happened. That is true. Let me keep this as the threshold as 1000 because 500 is too much. Okay, now I'll show you how exactly this works. So I run the code, and if I am, yes, I will share the code in the chat. If I'm static C, I'll sit for a second without saying anything, okay? See, my mouth is moving only little, it's not detecting, but the moment I move my hand, it's detecting the motion, and it's drawing bounding rectangle. So it's drawing bounding rectangle wherever there is a collection of pixels that are detected, okay? And then this is saving those frames. So I don't have to check all the frames for anomalies, but I just need to check for these saved frames for anomaly, making the work very easy. Now let's play with the size of the FPS is frames per second. Now let's check with the, what is the FPS? I think it's 30, right? 30 frames per second, 30 or 60. But we are not saving all of them. We are only saving whenever this anomaly is detected. But let me just delete all of this, too many files. Okay, so now what will happen if I change this to, let's say, 5000? What do you think will happen? Will my detection be more sensitive or less sensitive? Why do you think it's more sensitive? Who says more sensitive? So I'll tell you what the 5000 is. 5000 is I am discarding those contours whose area is less than 5000, which means small movements will only bring small changes in the adjacent frames, right? So if I increase this number, I am making my system less sensitive. So let's run and see. Okay, so Now see, if I'm moving my head, nothing much is being detected because the contour area is not very big. But when I'm moving my hand, it's detected because there is too much movement happening here. So this is less sensitive. But if I want to make it more sensitive, even if you want to capture my blinking eyes, let's see what to do. So if I keep this, let's say 250, then I am capturing those contours whose areas are 250 or above, which is much, much more sensitive than 5000. So here you will even see my eyes blinking being captured. Let's try. Did you see my eyebrows are getting captured? You see my mouth, eyebrows are getting captured. It's so funny. So, but this is basically how you can manipulate basic algorithms to, detect what you want to detect. Now let's do one more thing. Okay, I have a video here which I got from YouTube. Where is that? I think it's this one. So here I just got this from YouTube. It's an actual real CCTV footage where a couple of guys are actually performing a burglary. Before running this video, let me share the code with all of you so that you can also run this with me. Okay. So I will split the code into two parts so that, so these are this is the first part because I can paste only so much text here in the chat box. Or rather I'll download it and I'll send it to you as a file. Yeah, I'll send the file right now. Yeah, so this is the file. So just use the code from the file. Now, if I want to have this video inspected, right? So there is, at I think 2 minutes or something, there is one more person coming in this video. So just go to this, and instead of video capture of 0, just put video, whatever is the video name, it's video.mp4. Okay, then it will detect the burglars from the video as if it's a CCTV footage. You see? So now it is very sensitive because my threshold is, I think 250 or something, no? But if it's amazing, right? It's such a simple algorithm. There is no fancy deep learning here at all. Tell me, where is deep learning? There is no deep learning involved. It's pure logic and it's working beautifully. But of course, as somebody mentioned, if you don't want to detect cats or dogs, you just want to detect people coming into your private space. If that's your goal, then this algorithm won't work. But of course, there are ways to, even manual ways to deal with that. But also you understand this is why deep learning was introduced. But it's fascinating. Let's change this to 1000. Okay. I'm going to change this to 1000. And I think if somebody has a video of a human and a cat in one frame, just try playing with this contour area threshold. And I'm sure you will be able to find a threshold where if you keep the threshold as a certain number, you will be able to detect the human moving, but you will not be able to detect the cat moving. I'm sure there is a threshold that you can play with and figure out. So that will be very cool if any one of you can just try that. But see, now I increase my threshold. My algorithm became very less sensitive. Only if this person makes vigorous movements, something will be captured. Otherwise, it will not be captured. You'll be blocked when small kid is burglar. Yeah, of course. Yes, that will be there. But see, only if this person is moving very fast, you are detecting. But now let's change it to a small number. Let's say 50. If this is 50, what would happen? See, now it's like, it's so vigorous that even minute changes are being detected now. So it's amazing, right? Simple algorithm. and real-time detection. And then you, in the CCTV, you just check for these anomalous incidents from the saved frames. But now I have these giant, huge number of frames, which I have to now delete. But it's very cool. So just an exercise for you. Please, try running this code for different cases of thresholds and different videos. I'm very, very curious to see what you get. I have some other videos here of like people walking. I have like a football video here. We can try that. Let's see. Footer.mp4. Let's see what happens. And here I think I will have to reduce this thing even further. And this is anyway not a CCTV like thing, right? Because there are so many things happening in a football match. But let's see what we get. Okay, I don't want this much. So 500. Yeah, this is not very good because it's not a static camera. People are being detected, but you see background is also getting detected because camera is also moving. Camera is moving means the background is changing. But if you have a static camera, you don't need any fancy algorithm. That is what the inference is. But I think we can wind up this session, guys. Thank you so much. We are at the end of the session. So I enjoyed learning about this one particular non-deep learning approach, because we know that deep learning is very cool. But sometimes we also want to know how proper mathematics work, right? And this is that. So guys, I have to leave now, but please, I know that you may have questions. So you can drop your questions at this email, hello@visuara.com. I'll be happy to answer, or you can email me at this. This will also be good. So for the folks who are in pro plan, please check out the section where there is a quiz section also added, where I have added a CV2, like a computer vision related interactive quiz. So just go through that, and the rest of the material will be uploaded in both. The recording, all of you will be able to access. But thank you so much, everyone. I'll be looking forward to meeting you again on Thursday, same time. So we'll continue with some cool applications of OpenAI, OpenCV. And after that, we will move on to RCNN, UNet, YOLO, RoboFlow. So thank you all. Take care. Bye.